Cunyuan will talk to us about invalidation safety.
So hello everyone. Today I'm going to introduce a type and effect system that can track permanent and temporary invalidation. So let's start with this motivating example. So our system is region-based, so that means that you can have some local regions, and after we leave the lexical scope of a region, then everything on this region will be released. So we use this expression, let region in, to allocate a new region, and it will bind the region handler to the variable R1. And later, we can have some data on this region. We call buffer.make of R1. Then we have a buffer on region R1, and we can put some numbers into it. And then we can also have a nested region. We call it R2. And later, we just call buffer.copy of R2 and XS. It will allocate a new buffer on region R2 and copy all elements from XS to YS. And finally, we call iter of XS. It will create an iterator on the buffer XS and passes it to the parameter function here. And inside the function body, we call clear of YS. So this program is fine because XS and the YS are pointing to different buffers on different regions, even though the numbers inside these buffers are different, are the same. However, if we forget to call the copy function correctly, and instead we assign XS to YS directly, then we will get into trouble, because now XS and YS are pointing to the same memory location. So if we have the clear of YS in the same place, then we will get into trouble, because it will remove all the data here, and it will break the structure of the buffer, and we will get a runtime error, or even worse, we will get undefined behaviors. So we must reject this program. There are many systems that can handle these cases, but many of them are based on linearity or uniqueness, which puts huge restrictions on programmers. So for example, here we have a lambda function, which executes two parameter functions one by one. And we have two lambda functions here. They capture the same mutable cell and update it inside their bodies. This program is fine, but in a linear type system, it will be rejected because we cannot have two mutable borrows simultaneously. And we also want a powerful type inference. That means that we want fewer type annotations, and we want to support implicit generalization. So for example, we want to remove the type parameter and remove the types for all arguments. So our solution is based on Boolean algebraic subtyping and the higher-ranked polymorphism. So we combine the subtype constraint solving and the bidirectional type checking. So in Boolean algebraic subtyping, we have type constructors, union, intersection, and the negation. So for example, type inf is positive infinity or negative infinity. So here, positive infinity and the negative infinities are single types and then have corresponding values. And for real numbers are numbers that are not NaN and not inf. And we use the effect system. So we use this notation to say that a term E has type T, and it will raise an effect phi. And for a function, we say that this f consumes a type S and produce an T. And during the execution, the function body will raise an effect phi. So we put the effect inside this bracket. And if a term is pure, or say it has no effects, then the effect type will be bottom, the subtype of all types. And like other effects and region system, we can guarantee the permanent invalidation safety. That means that all the downlink references are unusable. If something belonging to a region is leaked outside, then all the operations on these objects is invalid. And we can also have disjointness reasoning for effects. So we say two effects, phi1 and phi2, are separated from each other if and only if the intersection of phi1 and phi2 is less than bottom. And we also claim that subtyping is important because we want to avoid poisoning problem. That means that if we have multiple subterms, their effect will not pollute each other. And we also want to avoid unnecessary effect coercion. And it also allows us to have fewer type parameters and smoother experiences. And we already introduced what is permanent invalidation. So what is temporary invalidation? It is similar. So we have reference, some references will become unusable temporarily, and later they will become valid again. So let's see this example. So we have a freeze function, which will suspend all the operations on the given region, which has type region of R, and then executes the parameter function here. So notice that this parameter function has effect E, which is for quantified here. That means that we can have arbitrary operations we want. But we have this and not R, which means that this E should not involve R, and inside this lambda function, we should not touch the region we suspend here. And we can have more advanced use cases, which may require higher ranked polymorphism. We will see later. And let's go back to this motivating example. So when we allocate a new region, we also allocate a new fresh abstract type variable. So this variable R1 is rigid. That means that we cannot make any assumption on this type variable. And similarly, we have another abstract type variable alpha2 for the region R2. And we also have this evidence, the intersection of alpha1 and alpha2 is less than bottom, to say that, OK, R1 and R2 are two different regions. And for all elements allocated on a given region, they will also carry this type variable. So for example, ys has type buffer of int and alpha2. So int indicates the type of elements we store inside this buffer, and alpha2 indicates where this buffer is allocated. And for the iterator, it, inside this lambda scope, it has type iter of int and gamma. So int is similar, and because the iterator is also mutable, so we also need to check where this iterator is allocated. So we have this type variable gamma. However, we do not know where this iterator is allocated, because it is allocated by the iter function, and from the perspective of users, we do not know. So this lambda function must have the ability to handle iterators from arbitrary regions. So this gamma must be for quantified in this scope. And finally, if we have operations on a region, we will also use the abstract variable for the effects. So for example, the clear of ys, it returns nothing, so the type is unit, and it has effects alpha2 because we are manipulating region R2. And to guarantee the temporary invalidation safety, we must satisfy this subtype constraint. The left-hand side is the effect of the function body, alpha2 here. And the right-hand side is either gamma. That means that we can freely use the iterator inside the function body, and a fresh type effect variable phi that is not alpha1. That means that when we're iterating over the xs, we cannot touch the corresponding region. So we will also output this phi for the effects of the whole application. However, if we forget to call the copy function, then this time ys will have type buffer of int and alpha1 because it's now pointing to a buffer allocated in region R1, and the clear of ys will have effect alpha1. And this subtype constraint will fail because alpha1 is not something that's not alpha1. So we will reject this program correctly. And let's try to make this example a bit more complicated. We keep this piece of code. We have a nested region, R2, and we create another buffer on this region, and we try to iterate over another buffer, xs, and during the iteration, we call the clear of ys. But this time, let's put this piece of code inside the function body. So now xs is an argument buffer. So the question is how to type check this function definition, because now we don't know what outer regions are, and we cannot have the evidence like what we did previously. And this function f must be available to use in arbitrary environments with arbitrary outer unknown regions. So the solution is to introduce our outer variable. So we call it omega, and it is for all quantified when we have this polymorphic function f. And this omega indicates all the unknown outer regions. So for the xs, it has type buffer of int and beta, where beta is less than omega, to say that this buffer is allocated in some outer unknown regions. And for R2, we also have this evidence. the intersection of alpha 2 and omega is less than bottom to say that this region is different from all outer unknown regions. And if we use fx inside this context, where we have two outer regions, R0 and R1, and they have type region of alpha 0 and the region of alpha 1, respectively, and we have this buffer, xs, which is allocated inside region alpha 1. And if we call this function inside this context, we will substitute all the omega by the union of all abstract type variables for regions. So for example, here, we need to instantiate beta with alpha 1, and we'll also have alpha 1 is less than the union of alpha 0 and alpha 1. And similarly, we'll do the substitution for this evidence. And finally, f of xs returns nothing, and the effect is alpha 1 because we are trying to iterate over this buffer. And finally, a quick summary of our contributions. So the key design of our system is the combination of Boolean algebraic subtyping and high-ranked polymorphism. So, and we introduce the outer variables to correctly abstract the unknown outer regions. And we can support various extensions like scope-safe metaprogramming and exception handlers without changing the core type system. And that's all of my presentation. Thank you for listening.
All right, we'll take some questions.
Thank you for the talk. Could you go back to the place where you introduced the iterator for the first time with the new region, the gamma? I was curious about this constraint because you said that you had one example. Thank you. You had one example which was satisfied, this is fine.
Yep.
And I didn't understand this because you said that, well, gamma is for all quantified from the iterator. And now you have a constraint that gamma is, you have a subtyping constraint here. How is this satisfied here?
Yeah, so basically the right-hand side is a union type. So basically you need to satisfy either left-hand side or right-hand side.
Oh,
so alpha 2 here is definitely not gamma because gamma is too abstract. So it must satisfy the right-hand side, the phi and not alpha 1. So if we have alpha 1 is less than not alpha 1, then we will get into trouble. So if we already have this alpha 2 is less than not alpha 1, then we will have, then this is equivalent to the evidence we have here. So it can be solved without any problems. And this phi is a flexible type variable. Then later we will see that we can use alpha 2 to constrain this phi, and later we use this phi to describe the effect of the whole application.
Okay, thank you very much.
Yeah, thank you.
Hi, thank you for the talk. You mentioned at the end scope-safe metaprogramming or an application of this to that. Could you elaborate on that a little bit?
Yeah, so we follow the similar idea. So for example, we have the metaprogramming inside how to say that? We have a multi-stage programming. We need to allocate a next stage variable. And when we allocate the next stage variable, then we increase, then we also have this abstract type variable for it, and you can only use inside the lexical scope. So you can use, we guarantee that it will be bind, and we will not have open code that can be executed.
I see. Thanks.
Yeah.
Next speaker, please come to start setting up.
Thank you. Thank you. So somewhat related to question to, the previous question. So I'm interested in staged programming, and so adding effect information to code generation means that so it's safe to run program at runtime, like eval function, or it's okay to safely store code fragment to mutable state.
Sorry, I don't understand
maybe we can discuss.
Yes, we can discuss later.
Okay, let's thank the speaker again.